solutions and colligative properties, some of the topics we discussed in our last lecture. These topics are thermodynamic calculation of molar elevation constant, measurement of elevation in boiling point, depression in freezing point, derivation of the expression for depression in freezing point. Today we will continue with the depression in freezing point with the help of some examples. Then we will proceed with thermodynamic calculation of molar depression constant, measurement of freezing point depression, and another important colligative property known as osmosis. First, we are considering some examples related to depression in freezing point. What is the freezing point of a 0.25 molar solution of glucose in water? Kf for water is given as 1.86 degrees Celsius per molality. As you know that delta Tf is equal to Kf into molality and delta Tf is equal to freezing point of solvent minus freezing point of solution. Hence, delta Tf solution will be equal to freezing point of solvent minus Kf into molality. Putting all these values here, we will get Tf of solution equal to minus 0.46 degrees Celsius. We have taken the freezing point of water as equal to 0 degrees Celsius. There is another example. What is the freezing point of 0.150 grams of glycerol in 20 grams of water? Again, you can use the same expression as delta Tf is equal to Kf into molality. As the weight of the glycerol is given, you can convert the weight of the glycerol into number of moles of glycerol by dividing the weight of glycerol by its molecular weight. And you can also convert the grams of solvent into kg of solvent. Putting all these values in the relationship, you will get the freezing point of solution as minus 0.151 degrees Celsius. We can also calculate molecular masses with the help of some examples. By dissolving 13.6 grams of a substance in 20 grams of water, the freezing point decreased by 3.7 degrees Celsius. Calculate the molar mass of the substance. Molar depression constant of water is equal to 1.863 Kelvin kg per mole. You can use the same expression delta Tf is equal to Kf into molality. Molality will be equal to moles of solute divided by kg of solvent. By rearranging that expression, you will get molecular mass of solute equal to 1000 into Kf into Wa upon Wb into delta Tf. Here, Wa is the mass of solute and Wb is the mass of solvent. Delta Tf equal to 3.7 degrees Celsius. By putting all these values, you will get Ma is equal to 1000 into 1.863 into 13.6 divided by 20 into 3.7, which is equal to 243.39 grams per mole. On dissolving 0.25 grams of a non-volatile substance in 30 ml benzene, here density of benzene is given 0.8 grams per ml. The freezing point of the solution decreases by 0.40 degrees Celsius. Calculate the molecular mass of non-volatile substance. Kf for benzene is given 5.12 Kelvin kg per mole. Now weight of solvent will be equal to volume into density. As density and volume both are given, we can calculate the weight of benzene, which is equal to 30 into 0.8 equal to 24 grams. Value of Kf for benzene is also given 5.12 Kelvin kg per mole. Wa, that is weight of solute, is equal to 0.25 grams and delta Tf is equal to 0.40 degrees Celsius. Putting all these values in the expression, Ma is equal to 1000 Kf into Wa upon Wb into delta Tf, we will get Ma is equal to 133.33 grams per mole. Molecular mass of the solute can also be calculated with the help of this example. A solution of 1.25 grams of a certain non-volatile substance in 20 grams of water freezes at 271.94 Kelvin. Calculate the molecular mass of the solute. Kf is given as 1.86 Kelvin kg per mole. As you know that freezing point of water is equal to 273 Kelvin. Hence, delta Tf will be equal to 273 minus 271.94, which is equal to 1.06 Kelvin. Now, by using the relationship Ma equal to 1000 into Kf into Wa divided by Wb into delta Tf, by putting all these values, you will get Ma equal to 109.66 grams per mole. Let us come to the thermodynamic calculation of molar depression constant. Molar depression constant is the property of solvent. It depends upon the nature of the solvent and it can be calculated thermodynamically by using the expression Kf is equal to RTF square divided by 1000 into LF. Here Kf is molar depression constant, R is universal gas constant, Tf is normal freezing point of the solvent in Kelvin, and Lf is the latent heat of fusion of the solvent. You must remember that the units of R and Lf must be similar. If you are using R in calories per Kelvin per mole, the units of Lf, that is latent heat of fusion, must also be in calories per gram. For water, the freezing point of water is 273 Kelvin. Hence, putting all the values in the expression, Kf is equal to 2 into 273 whole square upon 1000 into 80. 80 is the latent heat of fusion of water in calories per gram. Kf for water will come out to be 1.86 Kelvin kg per mole. In this table, you can see the molar depression constants for some of the common solvents. For water, it is equal to 1.86 Kelvin kg per mole. For ethyl alcohol, 1.99 Kelvin kg per mole. For chloroform, it is 4.70 Kelvin kg per mole, and similarly, you can see the values for molar depression constants for carbon tetrachloride, benzene and camphor also. For the calculation of molar depression constant, we can have a look on an example. A solution of 0.124 grams of a substance X in 25 grams of ethanoic acid has a freezing point 0.324 degrees Celsius lower than that of pure acid. The freezing point of pure acid is 16.6 degrees Celsius. Calculate the molecular mass of X given that the specific latent heat of fusion of ethanoic acid is 180.75 joules per gram. Now we have to calculate molar depression constant first. We know that Kf is equal to RTF square upon 1000 Lf. Remember that Lf is given in joules per gram, hence you have to use the value of R in joules per Kelvin per mole, which is equal to 8.314 joules per Kelvin per mole. So putting all these values in the relationship, we will get Kf equal to 3.86 Kelvin kg per mole. Now we have to calculate molecular weight of the substance. Applying the expression delta Tf is equal to 1000 Kf into Wa upon Ma into Wb. Wa equal to 0.124 grams, Wb equal to 25 grams, delta Tf equal to 0.324 degrees Celsius. Thus, the molecular mass of X is 59.09 grams per mole. If Kf, Wa Wb and delta Tf are known, then the molecular mass of the solute can be determined. As compared to elevation in boiling point, depression in freezing point can be measured more accurately and with less difficulty. Normally, two common methods are used for this purpose: Bakeman's method and Rast-Camphor method. First, we are going to discuss Bakeman's method. The apparatus for Bakeman's method consists of a freezing tube with a side arm to contain a solvent or solution. The solute can be introduced through the side arm. An outer larger tube into which is fixed the freezing tube. The space in between providing an air jacket which ensures a slower and more uniform rate of cooling. A large jar containing a freezing mixture, example ice and salt, and having a stirrer. 15 to 20 grams of solvent is taken in the freezing point tube and the solvent is allowed to cool. When it freezes, the temperature is noted. It is the approximate freezing point of the solvent. When the temperature falls within about 1 degree range of the freezing point, it is placed in the freezing mixture. Now it is cooled slowly. When it has come down to within 1 degree range of approximate freezing point, take out the tube, dry it and place it in the air jacket. Again, try to cool it. When it is 0.5 degrees below the freezing point, start stirring constantly. The temperature will raise up because latent heat will be set free. Note the highest temperature recorded. This will be the accurate freezing point of the solvent. Now remove the solvent tube, add some weighed amount of solute and record the freezing point of the solution again with similar process. By the difference of the freezing point of pure solvent and that of solution, we will get the depression in freezing point. By using the expression delta Tf equal to 1000 into Kf Wa upon Ma into Wb, we can get the value of Ma by putting all the values of delta Tf, Wa, Wb and Kf. This method gives accurate results if some precautions are taken. The supercooling should not exceed 0.5 degrees Celsius. The stirring should be uniform at the rate of about 1 movement per second. The temperature of the cooling bath should not be more than 4 to 5 degrees below the freezing point of the liquid. Now we are going to discuss the Rast-Camphor method. Rast-Camphor method is used for the determination of molecular masses of those substances which are soluble in molten camphor. Pure camphor is powdered and its freezing point is determined with the capillary method. In this method, capillary is used which is sealed at the upper end and the freezing point is recorded in a glycerol bath. When the freezing point of pure camphor is recorded, the camphor and the weighed amount of the solute is taken in a test tube which is sealed at the upper end and it is melted. After that, it is cooled and again crushed to the powder. Now this powder is again introduced into the capillary which is sealed at one end and its freezing point is again recorded with the help of ordinary thermometer. As Kf value for the camphor is very large, hence depression in freezing point for the solute is so large that ordinary thermometer can be used for this purpose. Nowadays, electrical apparatus is used for the recording of freezing point of camphor as well as that of solution of non-volatile solute and camphor. After recording the freezing point of camphor and that of the solution, we can get the depression in freezing point by the difference of the freezing point of these both. By the use of the equation delta Tf is equal to Kf into molality, that is delta Tf is equal to 1000 Kf into Wa upon MA into WB, the molecular mass of the non-volatile solute can be determined. Rast-Camphor method can be better understood with the help of an example. A sample of camphor used in the Rast method of determining molecular masses had a melting point of 176.5 degrees Celsius. The melting point of a solution containing 0.522 grams camphor and 0.0386 grams of an unknown substance was 158.8 degrees Celsius. Find the molecular mass of the substance. Kf of camphor per kg is 37.7. We can use the expression delta Tf is equal to 1000 Kf into Wa upon Ma into Wb. Here delta Tf will be equal to 176.5 minus 158.8, which is equal to 17.7. Kf is given as 37.7, Wa equal to 0.0386 grams and Wb, which is the weight of solvent, is equal to 0.522 grams. By substituting all these values in this equation, we will get Ma, that is molecular mass of solute, equal to 157 grams per mole. Now we are going to discuss some applications of depression of freezing point. Depression in freezing point has many applications in day-to-day life. It is used to clear the roads in severe winters. When salt is added to the ice, its freezing point gets lowered. If the freezing point falls below the ambient temperature, ice melts. But if the ambient temperature is below than that of the salt solution, then the salt will have no effect. Depression in freezing point is also useful in antifreeze. Ethylene glycol is used in the car radiators as antifreeze to prevent the water from freezing. There is an example in which we are using ethylene glycol as an antifreeze. Estimate the freezing point of an antifreeze mixture which is made up by combining 1 volume of ethylene glycol with 2 volumes of water. Density of ethylene glycol is given as 1.11 grams per centimeter cube and molecular mass is also given as 62. We can assume that 1 liter of glycol and 2 liters of water is used. The mass of the glycol will be 1.11 kg and that of the water will be 2 kg, so that the total mass of the solution will be equal to 3.11 kg. Now number of moles of glycol will be equal to mass of glycol divided by its molecular mass, which is 62. So number of moles of glycol will be equal to 17.9 moles. Molality of glycol will be equal to number of moles of glycol upon kg of solvent. Solvent is used 2 kg, hence molality of glycol will be equal to 17.9 upon 2, which is equal to 8.95 mole per kg. As we know that delta Tf is equal to Kf into molality, therefore delta Tf will be equal to 1.86 into 8.95, which is equal to 16.6 Kelvin. Now the freezing point of pure water is 0 degrees Celsius, hence the freezing point of this solution will be equal to minus 16.6 degrees Celsius. There is another very important colligative property known as osmotic pressure. Osmosis has been derived from the Greek word osmos, which means to push, and this phenomena was first observed by Abinollet. It has also been observed that if through semi-permeable membrane is placed between dilute solution and concentrated solution, the solvent molecules migrates from dilute solution side to concentrated solution side. Osmosis is defined as the spontaneous flow of solvent molecules from solvent to the solution side and also from dilute solution to concentrated solution side. The phenomena of osmosis can be demonstrated by a simple example. 2 eggs of the same side are taken and their outer shell is removed by dissolving in hydrochloric acid. One of the eggs is placed in distilled water and the other in saturated salt solution. After sufficient time, it is noticed that the egg placed in water swells up and that placed in salt solution shrinks. In the first case, water enters the concentrated egg fluid, while in the second case, water comes out of the egg as salt solution is more concentrated than the egg fluid. Let us discuss about semi-permeable membranes. Semi-permeable membranes allow the passage of some of the particles while blocking the others. There are some naturally occurring semi-permeable membranes like cell membrane and egg membrane. There are some synthetic semi-permeable membranes also like cupric ferrocyanide and phenol. We can prepare semi-permeable membrane in the laboratory. For example, cupric ferrocyanide. Cupric ferrocyanide membrane deposited in the walls of porous pot is perfectly semi-permeable and is used for accurate experimental work. An unglazed porcelain battery pot filled with copper sulfate solution is placed in a solution of potassium ferrocyanide, that is K4FeCN6. The two solutions permeate into porous walls of the pot from opposite sides. A gelatinous precipitate of cupric ferrocyanide is formed in the middle of the pores of the walls. In today's lecture, we discussed the thermodynamic calculation of molar depression constant. In this, we used the expression Kf is equal to RTF square upon 1000 into Lf. We also discussed the measurement techniques for depression in freezing point, where we discussed two techniques, Bakeman's method and Rast-Camphor method. In last, we defined osmosis, and in our next lecture, we will continue with the discussion of osmosis and osmotic pressure.